Hey everybody, this video is about work. So I have the textbook definition right here, which will take some explaining. So let's start there. So let's say you have a box and then you want to push the box with some force. Let's say 5 newtons. And you want to push the box from point A to point B over here. Let's say that's 3 meters away. Okay, the work is this force dot the displacement. So let me pick a coordinate system. I'm going to purposely off on the side over here. So the position of the box at point A is like this. Some vector, I'll say RA, the position. And then the position of the box at B is some other vector. I'll call it RB. So the displacement is the difference, right? This vector minus this vector, which is this displacement vector here. Call it delta R. So the work is this dot this. So if I write this force, I'll call this force F. So the work from A to B is F dot the displacement. And then when you take a dot product, you get a scalar, right? This is a scalar. And the unit is joule. Okay, so that's work. Now let's change it up a little bit. So let's say you apply a force like this. Okay, let me just make up some numbers. Let's say it's 5i minus 4j. So now what is the work by this force? It's this dot this. Right, so if I make this say that's 3 in the I direction. So you take the dot product, it would be the x component times the x component plus the y component times the y component of this is 0. So now this would be 15 right here, plus, let me write it out, 5 times 3 plus -4 times 0. So 15 joules. So notice this component of the force didn't contribute to the work. Only the component of the force parallel to the displacement. Okay, now let's say you're pushing the crate along and then there's a ramp over here and then you want to go over here to point C. So then all you would do is the work from A to B in joules plus the work from B to C in joules. That's it. All right, now let's say the path is like this. You want to get from here to here, applying a force like this. So how would you do it? You could just break this up into like little segments like this. And then you go, let's say displacement 1 over here, delta R1, and then delta R2, and then delta R3, until you have however many of them, n of them, delta Rn, and you just add them up, right? So the work would be add them all up. Sum F dot delta R1 through n, like this. And then now we kind of use calculus a little bit. So these displacements, you make them infinitesimally small. So they're no longer just discrete displacements. They're differential, like instead of delta R, dr. Infinitesimally small. And then F dot that dr. And instead of this sigma for a sum, it's like this. And look, that's exactly the definition here. And that's the trick to it. Okay, now let's have maybe a simple example. Let's say there's a ramp, and then there's a block of mass m, and let's say it's smooth, and let's say the block slides down 3 meters. Okay, to over here. What's the work done by gravity? Positive, negative? So here's the free body diagram. There's a normal force, the weight, and let's say we pick coordinates like this. Let's try this 2 different ways. How about and then like this. Okay, let's get the geometry in here. So the angle is here, so here and here. Okay, what is vector n? Well, maybe I'll just call this the weight, W. If the normal force is this way, and the displacement is this way, what's the work by this normal force? 0, right? Because this force dot this displacement, they're perpendicular, so the dot product is going to be 0. The normal force is not doing any work at all. Okay, what about the weight? So according to this coordinate, it would be in the negative y direction, so negative, like this. And then the displacement, I'll just call it vector d, would be in the x direction, 3 cosine theta, in the y direction, negative 3 sine theta. So the work by gravity would be, I'll just say 0I. Right? This times this plus this times this. So the work would be 3 mg sine theta joules. Right? So positive. Okay, how about if we pick this coordinate system? The displacement would be 3I, right? Because look, it's this way. And that's the way I picked the x-axis. The weight would be, in the x direction, mg sine, and in the y direction, minus cosine. Okay, and then if we solve for the work, it's this times this plus this times this. So the work would be 3 mg sine theta joules. Same, right? So you pick your coordinates however you want to make the math simpler for you. And in either case, we got the work being positive. And then if you think of it maybe simpler, like just vertically, if you had a block and you, let's say you apply a force this way, and then the block moves up, right? Then are you doing positive work or negative work? The force is going up, the displacement is going up, you take the dot product, it's positive. And then how about the work by gravity? So the weight is this way. So if the displacement is going up and the weight is going down, if you're lifting something upwards, gravity is doing negative work, right? Because the displacement is up, the gravity is down. If you lower an object, so then the displacement is this way, and the gravity is that way also, then when you lower something, gravity is doing positive work. Okay, so I'll let you think about that, let that marinate in your brain. Okay, now let's do one more example. If the force is variable, so instead of a constant force, what if the force is variable? And the perfect example we have is a spring. So let's say you attach a spring to a wall, and then you show up, I'll just draw it like a cartoon here, and you pull the spring, so you stretch it. So it's initially, let me pick coordinates, let's say it's initially here, some initial position, and then later here. So the displacement is this vector right here. I'll just call it generically delta r for displacement. The spring force is proportional to the displacement, but in the opposite direction. Okay, so this minus sign is because if the displacement is toward the right, the spring force is to the left. If you show up and you smash the spring, and the displacement is toward the left, the spring force would be toward the right. That's why the minus sign. And this constant of proportionality is the spring constant. And if you just look at the units, right, that's newtons, that's meters, so the spring constant is newtons per meter. Okay, so this is called Hooke's law. Now, what about the work by the spring? So let's make this a little bit simpler. I'm going to move my coordinate system right here. So the origin is just where the spring is in its unstretched position. So then I can say my initial position is 0. So now, that way now the spring force is just minus kx, like this, right? But this is 0. So the work, again, is F dot displacement. Here's F, and that's in the I direction, dot, oh, this should be dr. Let me split up the displacement into components. Okay, now what happens when you do this dot product? X component times X component plus Y component times Y component plus Z component times Z component. So this just simplifies to like this. Right? And then if we just integrate from somewhere to somewhere, initial to final, let's make this 0 even. Right? Then the work by a spring is, we just integrate this, minus x squared over 2. I'll just leave it like this. Minus k x squared over 2. Okay, so this is the work by a spring in joules, right? So notice it's minus. Okay, so give a few of these problems a try and practice, but really the problem solving will come soon. We need to introduce energy. So we'll do potential energy, kinetic energy, and then we combine all of that into a technique to solve problems. So this is kind of only step 1. So stay tuned for those videos, and I'll see you on those.